start. So we can go ahead and get started at this point. It's a real pleasure for me to host the talk today. Our speaker is I Sen Chen, I Sen Chen, from the Department of Philosophy at Soochow University. So I'm going to keep my introduction relatively short so we can give as much time as possible to I Sen. So please go ahead.
I'm very honored that Yangming Xingze gave me the opportunity to share my work with you all. So this is the title of my paper or my presentation today, The Indispensability of Representation to Machine Learning. From seeing the title, you might feel that I want to do something very ambitious. Yes, indeed. So let me show you why it is so ambitious. Okay, thank you. So representation is the view that intelligent agents are capable of being in mental state with representational content. Typical cases are belief and desire. And I would like to say that representationalism has been one of the foundational theory or pillar of contemporary cognitive science. However, since 1980s, many philosophers have argued against representationalism and held that cognitive science should be replaced by computational neuroscience. So, for example, Stephen Stich and Paul Churchland. And I will call this position eliminativism. Okay. Now, here is a very important thing I want to discuss with you. This is called the indispensability argument. So, it has been part of the standard procedure for establishing the existence of something to argue that it is indispensable to our best scientific theory. Right? So this is something that Quine gave us. Right? He said, well, if you think that, well, if you can argue that something is indispensable to our best science, then we should have ontological commitment to it. So here is the argument. We ought to have ontological commitment to all that is indispensable to our best scientific theory of the mind, of course. And the second premise is that representations are indispensable to our best scientific theory of the mind. Therefore, we ought to have ontological commitment to representation. So this is the indispensability argument. However, in today's talk, my argument is to argue for the claim star, which only says representations are indispensable to the science of machine learning, rather than the best science of the mind. Okay, so notice the difference here, the claim star, where I say representations are indispensable to the science of machine learning. And here, the premise here is representations are indispensable to our best scientific theory. So this is different. I want to say that if my argument is correct or successful, then the claim star could lay the groundwork for a complete indispensability argument for representation. So in this sense, this is not very ambitious, but already ambitious enough, I guess. All right. Okay. So here's the plan. I will review previous attempts for or against the representations in cognitive science. And second, I will introduce the basic principles of convergent machine learning. And third, I will argue that representations is indispensable to machine learning. And finally, I will discuss some objections. Okay. So let's begin. Section 1, cognitive science, classical or connectionist. This is to be a common place for a lot of people in this room here. Presumably, I would say, our best science of the mind is cognitive science, right? In contemporary context. And cognition is highly interdisciplinary and heterogeneous. Classical computationalism claims that cognitive processes are always mediated by symbols. And cognitive neuroscience or connectionism would say that cognitive processes are explained by the firing patterns of neurons. Or if you're talking about real neural network. Or if you are talking about artificial neural network, then we will call them unit, right, rather than neurons, without positing symbols. While it is generally agreed that representations are indispensable to classical models, it is controversial whether or not they are in the connection system framework. Now, here is an, I would say, unsuccessful attempt for arguing for representationalism. Representationalists point out that when cognitive organisms perform a particular kinds of tasks, for example, visually tracking and reaching for prey, okay, like frog tracking the flies. The proximal input, namely the retinal stimulation patterns, could be very heterogeneous because, you know, seeing from this side, from that side, from that side, the retinal stimulation pattern could be very different. Right? However, they can still recognize that this is the same object, right? So they can still track the fly. And sorry. So the proximal input are heterogeneous, even if the distal objects remain the same. So what is interesting is that although the proximal inputs are heterogeneous, Frog can reliably recognize the distal objects as fly and respond appropriately. As he demonstrates by adopting the representational standpoint, cognitive neuroscientists can capture the interesting pattern that unify the heterogeneous causal processes. Okay. So he says that, well, we need representational talk or representation talk because it can capture some interesting causal processes that is not recognizable if you just focus on the neural firing pattern. Nevertheless, some people want to say, the fact that scientists are use of expressions does not establish the indispensability of the entity denoted by the expression, since the expressions might be paraphrased. So here is an example I want to give you. Suppose we have a claim A, which says the average family has 5 children in the society S. Claim B says family A has 6 children, family B has 5 children, and family C has 4 children in the society S. As you can see immediately, instead of providing explanation on its own, claim A is merely a summary of B. So if I would want to say this, if A and B can explain the same thing within the same theoretical framework, and A is merely a summary of B, then we can say A can be paraphrased by B, and therefore A is dispensable. So, let me see. Yeah, so this is William Ramsey's argument against representationalism within the connectionist framework. He said this: to be sure, the task of cognitive neuroscientists is to explain the role of cognitive state plays. As he says, on the surface, cognitive neuroscientists assign representational content to neural states corresponding to their cognitive roles or causal role, however you like to call that. However, the same cognitive role can be explained totally by the firing pattern of neurons and thresholds and weights of the whole framework, the whole network. So in the connectionist framework, the representational fact about a neural state merely summarize its cognitive, the neural state's cognitive role, which is in turn fully explained by distribution of weights and threshold and the firing neuron. So in connectionist framework, representational talk is actually can actually be paraphrased away. Similarly, another philosopher I really admire, Francis Egan, she claimed that representational talk is merely scientific gloss. So according to her account, the notion of representation is useful simply because it helps scientists understand why and how an agent performs a cognitive task. And her view is that the indispensability of representation is merely for technical reasons. Why? Because suppose yes, our explainants uh, compose only causal talk, right? Neural talk. But our explanandum is about behavior or desire, that kind of thing. Then we really need a bridge principle to connect the causal talk to the representation talk. So her view is that representation talk is indispensable merely for technical reasons. But this kind of indispensability does not deserve our ontological community. Right? So here is the summary. Summary one, despite their superficial difference, Ramsey and Egan's view have a common core. I will put it this way. If representations are really indispensable, right, dispensable in the sense that deserve our ontological commitment, then they are not merely summaries or simplifications for the role of cognitive state. Rather, they have to explain the role. Right? Representation, content, they are posited because we want to use content to explain the cognitive role of the state. Now here is I would say a successful argument for representationalism. So this is the same guy, William Ramsey. He argued that a problem-solving machine, say a chess player, has representations. And his example is borrowed from Newell and Simon's physical symbols machine. So let's think about the famous missionary cannibal problem. Okay. So I don't know if you played this game before. So suppose there is a river. We have two banks, and there are three missionaries, three cannibals, and you have to move all of them to the other side. But there is a rule: at no time can you leave the number of cannibal more than the number of missionaries. Otherwise, they will be eaten by the cannibal. Okay, that's the rule. And Newell and Simon, their suggestion, if we want to have an AI to solve this problem, and the first step is to construct a search space. So here is the search space. So you can see that we have two banks, right? At the first, we have three missionaries, three cannibals. The other bank is empty. And in the end, we want to move all of them to the other side. So this is the search space that contains all the possible routes from the starting state to the goal state. Okay, that's search space. And as Newell and Simon says, in order to get to the goal state efficiently, scientists need to give the machine heuristics so that you will not have to exhaust the entire search space and you can find the solution in the mechanical fashion. So here I give you two examples of heuristics. Rule number one: avoid immediately undoing any move. Okay? So if you move one person to the other bank, then in the next step, don't move it back. Right? Avoid immediately undoing any move. And rule number two: if it is possible to move only one symbol from the lower bank to the upper bank, check this possibility first before checking other possibility in which you have to move two symbols. Right? So this rule number two, helps the machine to find the solution more efficiently. So Ramsey says this. The search space plays two very important roles. First, it serves as the model for representing the possible state of the situation. Second, it serves as the semantic content of the machine's symbol system. Okay. Similarly, we also need the heuristic for interpreting the symbol manipulation rule of the problem solver. Okay. So these two roles are indispensable to explaining the reliability of the problem solver. Okay. So in this sense, we can say it is very similar to truth conditional semantics of mathematical logic. Right? Tarski models are involved to interpret the symbols and the Boolean function, meaning conjunction, disjunction, implication, negation, are invoked to interpret or explain the inference rule. Of course, the whole process would be described purely syntactically, okay? But this is not how explanations are done in classical logic and classical AI. In the classical framework, representations are invoked to explain the causal roles of the symbols and not merely summarize the causal roles of the symbols. They play the genuine role of explanation. So it is indispensable. Okay? But now we have a problem. Let me see. Okay, I still have a lot of problems. Although Ramsey's argument is forceful, in my view, there is one aspect of his case study that is particularly unsatisfying. Namely, the problem solver is a symbolic machine. Suppose, first, Ramsey's argument is the only indispensability argument for representationalism. And second, it turns out that human cognitive processes are not mediated by symbols. Then the indispensability argument for representationalism is undercut. So here is the summary, another summary. Ramsey provides an argument showing that representations are indispensable to classical theories. And this argument takes advantage of the fact that classical theories involve search space and heuristic to explain cognitive processes. And this argument presupposes the existence of symbols. So we want an argument that has A, but we don't want to have B. Can we have that kind of argument or case study? I claim that we can. So now I'm moving on to the second part. So I put a notes here. Tell me where we are. Where are we? Convergentist machine learning concerns how machine can learn reliably. Its theoretical foundation is actually statistical learning, or sometimes called statistics. And the end of which is to address the following problem. How can we select the correct hypothesis reliably? What do we mean by reliable here? The idea of reliability here is this. When the amount of data goes to infinity, then the agent eventually will select the correct hypothesis and never abandon. That's what we mean by reliability. Actually, you can also call it convergence. Okay, that's the same thing in our context here. Okay, sorry, convergence here. When the agent does select the correct hypothesis and never abandon it, then we say the agent converges to the correct hypothesis. So the concern of statistical learning, of machine learning, is about how an agent or machine to converge to the correct hypothesis given sufficient amount of data. And finally, we say a learning method or a learning algorithm is a function from data sequence to a hypothesis. Okay? So you give me a set of data, then I will select a hypothesis and output. So this is a learning method, a learning machine. Sorry. Accordingly, a learning machine is a machine which implements a learning algorithm. Okay? Oh, okay. Case number one, cat recognition. Suppose we want to build a learning machine that can learn how to classify cats visually from non-cat. So the data composed of a lot of photos, okay? Some of which contains cat's face, some of which does not. And we want to train the machine. Eventually, the machine know how to classify which photos cat face, which photos does not have cat's face. And this is an instance of typical so-called binary classification problem in machine learning. And the hypothesis to be selected is called a binary classifier. So we can see here, we can say these color dots, right? There are, or and then also these black dots, they are all photos. Only the black dot contains the space. Other photos do not contain space. And we want to find a classifier and a line like this that separate the data. And in this kind of problem, we want to find a classifier or the hypothesis or the classifier that best separates the black dots from the hollow dots. So hopefully, through training, the machine will select the classifier that best classifies the data. Case number two, temperature carbon dioxide. So let's think about a 3D space. X represents the amount of carbon dioxide. Y represents the size of the whole population of bees. And the Z represents the Earth, the temperature of the Earth. So we will have a lot of dots, right? These are the data in the space, in the 3D space. And the hypotheses in this case are 2D surface. And we say that the hypothesis that best captures the pattern between X, Y, and Z is the one that contains as many data points as possible. Okay. Again, what we want is a learning machine that can select the hypothesis that best captures the pattern as the amount of data goes to infinity. Here, I want to introduce to you what I call three levels of learning algorithm. I will call them the computational, the heuristic level, and the implementation level. Each succeeding level implements the previous one. And notice that all these three levels, including the last one, what I call the implementation line, are still at the software level. Okay, so they are not the same as Mars tri-level hypothesis. Okay, they don't concern the question of how to realize the algorithm physically. Okay. So first level, computational level. At the computational level, scientists are concerned about why and what question. For example, mathematically, is there a learning algorithm converging to the hypothesis that best captures the pattern? If so, what is the learning algorithm and why is it? That's the question to be addressed at this level. So most those statistical learning theories, they work at this level. They try to prove a lot of theorems showing that for this problem, the, a learning algorithm for achieving this goal is possible, etc. Now, I want to give you another important name called empirical risk minimization. So gladly or luckily, scientists have proven that under certain modest conditions, there exists a learning algorithm that converge to the correct hypothesis when the data set is big enough. And this is called ERM, empirical risk minimization. So let's think about what is ERM? What is empirical risk? So given the training data, consider a hypothesis. Suppose our hypothesis is a plan, right? Like what we just talked about before. It's a plan, and we have a lot of points in the space, okay? And those points are the data. Then we can calculate the vertical distance from the data points to the plan and call this distance E. And we take the square of E, namely E squared, right? And then for each data, for each of the training data points, we calculate its D squared, and finally we sum together all the D squared. Suppose this is our hypothesis, and we have a lot of data, and we're just summing together all the D squared. And this value is called empirical risk of the hypothesis. And empirical risk minimization as a learning algorithm requires this. When giving the training data set, the learning machine should always select the hypothesis with the least empirical risk. And the scientists, very beautiful, proved that under circumstances, by following ERM, when the amount of training data goes to infinity, the machine will select the hypothesis with the least empirical risk for all possible data, not just for the training data. And this result also holds for a CAT problem. Now, at the heuristic, let's move on to the heuristic stuff. ERM does not tell us how to find the hypothesis it recommends, right? As we know, it recommends the hypothesis with the least empirical risk, but it does not tell us how to find the hypothesis. Of course, we may try to calculate by hand. Right? For each hypothesis, we just calculate its empirical risk and comparing them, find the least hypothesis, right? But will be too time consuming. So we need a mechanical, stepwise procedure to find a hypothesis recommended by ERM. So the idea is that, the machine randomly select the hypothesis at the beginning before training. And then when the training data comes in, how should it proceed? That's the problem. How should it proceed to find the hypothesis with the least empirical risk? So again, we're going back to search space. Right? The idea to address this problem, to find the empirical risk hypothesis, but the standard practice to address this problem is to construct a search space for the learning machine. Okay? So let's assume that the training set only contains a single data point. Okay? And each hypothesis assumed has the following form: T equals A times U plus B times B. Here, T, U, V are all variables, like the amount of carbon dioxide, the size of trees population, etc. And the B and A and B are merely coefficient. Okay? So every hypothesis, they differ only at their coefficient respectively. So every hypothesis can be fully characterized by a unique point, A and B, on a 2D plane. Okay? Now, let's think about a hypothesis called F star. And let's just stipulate that F star is the hypothesis with the least empirical risk. And let's say P is a training photo. So F star of P is the answer that the classifier F star outputs about whether P is a photo of a cat or not. Right? And then for any other hypothesis, any other classifier, we compute the following value, F star of P minus FP, and take the square. This value measures how mistaken a hypothesis, the hypothesis F, is about the training data point P, compared to F star, which is the best hypothesis, as we know. And we can call this value the error of F. So now we can consider a 3D space. We stipulate that in the 3D space, every hypothesis is represented by a point on the XY plane. The Z-axis represents the error of the hypothesis. So every point in the 3D space represents a hypothesis and its error. And so pictorially, these points together form a curved space, which intersect the XY plane at exactly one point. And that point is F star. This is because by definition, the error of F star is 0, right? Because Oriol assumed that F star is the hypothesis with the least empirical risk. So this surface is actually the search space for the learning machine. So you can see, this is the search space of the learning machine. So the idea is that the learning machine will at the start and starting stage, so randomly select a hypothesis. And the bottom point, right, is the hypothesis, the least empirical risk. So the learning machine needs to somehow go going toward the bottom and find the hypothesis with the least empirical risk. So this is the I will call gradient descent. Now let's rephrase the problem, the question for machine learning scientists at the heuristic level. The machine starts with the random points on the surface, and its aim is to get to the bottom point, or the global minimum, in a stepwise manner. The global minimum, by definition, recall, is the hypothesis with the least empirical risk. So how might we accomplish this? One way is to follow what they call gradient descent. This is a heuristic. This is a heuristic to help the machine. Just like previously we have the missionary pineapple case, right? We have a very big search space, we need to give the machine some heuristic to help it to find the goal state or whatever the to reach this goal. So gradient descent is one of the most commonly used heuristics. Now, at the implementation level, scientists deal with how question with a particular machine type. Suppose the machine they have in mind is a feed-forward network, the most commonly seen kind of network. And we recall that we assume our hypothesis has this A times U plus B times B. This actually corresponds to a single layer network. Treating U and B U and B. C is the output. And here we have the error. And A is the weight. Also the weight. Coefficient N corresponds to the weight. So every hypothesis actually corresponds to an artificial neural network. Now, once we establish that every hypothesis can be represented by a network, and then we can implement it. We can implement gradient descent by a feed-forward network. And this finally gives us web propagation, the very famous learning algorithm as we know nowadays. Actually, you will tell a machine or a network how to adjust its weight in order to move downward along the search space to the mean to minimize this error, right? To find the hypothesis with the least individual risk. Now, let's move on to part 3. Move on to the part 3. Okay. 10 to, okay. Okay, according to the widespread view, I guess it's the widespread. That propagation revives behavioral idea of learning. So the idea is that the whole process can be explained simply in terms of stimulation and response without representation. So suppose the error is expressed by proximal input, say the force exerted on Y space by his or her teacher's slap, right? Because he or she answered the wrong question. Oh, sorry, saying the wrong answer to a question. Right? And so the student gets a punishment, and he will just adjust his weighted impression. So according to this widespread view, that propagation has nothing to do with representation. It is simply a causal dynamical equation describing how the neural network evolves. Now I want to say this picture is wrong. So earlier, we say that A, in truth conditional semantics of logic, Tarski model and Boolean function of representation, instruction, translation are the semantic function for interpreting sentences and input. Right? The classical AI, search space, and heuristics are the content for interpreting the symbol and the symbol manipulation. In both cases, the representation talk is involved to explain the causal role of those states or symbols, not merely summarize them. Now I want to say the same point can be made with respect to machine learning. We need a search space, right? In machine learning, we need a search space, and we also need heuristics, which is gradient descent. serves as the content to explain two things. First, why fat propagation is reliable. With why fat propagation will transform the network into a good network. Right? The network will adjust weight until it can answer questions or make classification very reliable. Very reliable. And the second is to explain why the state of the machine cause the state or cause another state of the machine in the way it does. That is what I call causal dynamics. So I want to say that search space and the heuristic tool, namely gradient descent, are the semantic content to explain reliability and the causal dynamics. Just like what we had earlier, we all have this semantic content to explain the reliability of logical rule and the causal dynamics of the symbol transformation. Okay. So first, let's think about explaining reliability. Consider we have a reliable learning machine. To explain why it is reliable, scientists would say because the machine M uses ERL, individual risk minimization. That is, we always select the hypothesis with the least individual risk. And this explanation obviously requires the machine M to be able to be in a state that represent hypothesis. So M has to be in the representation. Objection, some people might want to say, well, there is another sense of reliability which does not presuppose the idea, but the ability to have representations. For example, thermometer. We would say thermometer is reliable, but some people might want to reject the idea that the thermometer has representation. So some people might say, oh, there is another sense of reliability, namely dependable causal relation, or dependable covariation. My answer is this. Perhaps there is another sense of reliability that does not require replication. So this misses the fact that convergent learning turns the reliability in the epistemological sense, not the total sense. Recall that earlier we said the idea of reliability in convergent learning theory is that when the data goes to infinity, the machine will select the correct part or the best part. Right? So this is a clearly an idea of reliability in the epistemological sense. Explaining causal dynamics. To explain why, for example, after receiving a set of data, machine N state N causes it to be in another state. So the scientists would say that N represents a hypothesis, for example, Hn, and P represents another hypothesis, Hp. And the machine M tokening N, right, be in the state N, causes it to go into another state, P, because HP is closer in the search space to the hypothesis with the least empirical risk than HN. So the reason why the machine will start from H to P is because H is P, right? P is closer to the global minimum. Yeah, and again, another objection. There is always a purely causal explanation for the same processes. My answer is Well, the fact that M goes from N to P can be explained purely by backpropagation as a causal rule. But if we don't assign content to those states, then we cannot explain why backpropagation has its mathematical form at the end. Now, final part. Uh, Remarks and discussion. Convergentism versus connectionism. So to repeat, my end, my goal is only to argue that representation is indispensable to convergent machine learning. Okay? I don't want to say that it is indispensable to the best science of learning. I just want to, re-emphasize this. And connectionists or neuroscientists may object to convergentism. Why? Because typically bad propagation requires some neural mechanism that transmit the error signal from the output layer back to the input layer. But the neurological evidence is insufficient so far. So connectionists might prefer something like, heavier learning, right? Heavier learning does not require that kind of feedback neural mechanism. But my reply is this. A, there are some behavioral evidence for backpropagation. B, backpropagation is not the only way to implement gradient. We have another machine learning algorithm. It's called Boltzmann machine learning algorithm. It also implements gradient. And it also presupposes representation. But it does not require feedback neural mechanism. Objection number 2, Frege's model. Some people will have these objections. For some people, they will say that if someone is able to be in representational state, then that person must be able to suffer from Frege's model. That's I picked up from some philosophers 3 years ago. So if a machine can really be able to be in the representational state, then the machine should be able to suffer from Frege's model. So here's the question: is a learning machine able to be subject to Frege's puzzle? And that is the slogan: no representation without modes of representation. And my answer is there's no reason why they can't. So for example, we are training a machine to visually recognize a person, John. Okay. As it turns out, and it has been found in the industry, the machine learning industry, that the visual pattern extracted by the learning machine actually are highly susceptible to the environmentals, to some environmental factors. So suppose John, you take a picture of John on the sunny day or on the rainy day, then the machine might say, well, this is John, but the other one is not. Simply because the background information is different. So I want to say this: it would not be too far-fetched to say that the machine's concept, if I can say that, of John is not merely referential. It is also constituted by John's modes of representation. Furthermore, being subject to Frege's model is a sufficient condition, in my view, rather than necessary condition to having representation of state. For example, in the standard set theory, there are no proper names, so predicate cases do not arise. And we can think about hypothesize some mathematician who only knows that field, so who has no proper name in his or her mind. But that mathematician can still genuinely believe something, like believing some mathematical proposition. So my point is that uh, being subject to Greg's model is not necessary for being able to have representation. The final objection, conversationality as systematicity. So as you can see, in my whole presentation, I only talk about neural network, right? I didn't say too much about how machine learning works under a symbolic machine. I only talk about convergent learning, convergent machine learning, how it works within neural network. But if we are working under the framework of neural network, then we dispense with symbols now. But some people might have some problem about this, some issue about this. So here's the idea. If a learning machine has representation that can represent a hypothesis, then the contents are propositions. In philosophers' jargon, those representations are typically called thoughts. So machine can have thoughts. And thoughts are compositional. So any machine having thought must have symbols. And this was argued by Fodor and Hillerson in their very famous 1989 paper. They argued that, well, thoughts are composition. And so we need symbols. So learning machine can be implemented by neural network, which does not have symbols, but according to my view, which can be in representational state. So it seems that what I argue for here goes against Fodor and Hillerson. But here are my replies. Well, first, I want to say that this objection actually is just grist for the mill. Why? Because compositionality debate is about the format of representation. So it makes no sense at all to have a debate about the format of representation if you don't agree that we already have representation. So if you think that, so if you think that this argument or this debate is important, then you should already agree that machine can have representation. Secondly, I don't think systematicity or compositionality is necessary to having representation. Certainly not ontologically. So even if this argument, compositionality argument, is correct, it only shows that connectionism is a theory of physical implementation, not a theory of cognition. And it says nothing about whether our neural network can be able to, is able to be representation state, if representational state or not. So my point is that even if their argument is correct, my point, my claim is consistent with their conclusion. Okay, finally, brief summary for my talk today. In today's talk, I argue that representation is indispensable to converging to learning. At first, we visited the previous arguments for and against representation. I draw the moral that if representation is indispensable in the sense that deserve our commitment, ontological commitment, of course, it should explain cognitive process, not just summarize cognitive. Secondly, I introduced the basics of convergent learning theory. Thirdly, I argue that in convergent learning, representations are indispensable for explaining the reliability and causal dynamics of the state of the network. And finally, I address some two problems. Okay, so thank you, everyone.
Okay, so I think we'll take a 10-minute break at this point, and we'll resume in 10 minutes for Q&A.